All right, good afternoon, everybody. It is Sunday, August 31st, last day in August here. And I'm doing a retake of this video about doing the calibration for the EMPAD and the saturation current calculation because I realized I could do a couple things better. So, I wanted to do that. So we're going to go through this again, hopefully kind of streamline things a little bit here. So I did the videos already about collecting the EMPAD data and then visualizing the EMPAD data. The visualization in particular, after I did that, I realized I needed to retake this video about doing the calibration. So, we're going to do this today. So anyways, I have ImageJ open here. And so when I say calibration of the EMPAD, what I mean is, so your EMPAD data consists of diffraction patterns, each of them taken with 128 by 128 pixel resolution. Your diffraction pattern has a horizontal field width, which in terms of diffraction space, we usually measure either in terms of reciprocal length units or angles, okay? So the angles we typically use, give you an example here. So the angles we typically use are either, the numbers for angles are usually millirad, or as far as reciprocal length, usually reciprocal nanometers, okay, typically speaking. So to do the calibration, you need a standard. And so the standard that people use for a lot of calibrations is the gold palladium replica grating. So what I did was, and I showed you how to do this, I showed you how to collect the series data, not an actual EMPAD scan, but just like a series of 1,000 images in EMPAD. So that's what I did. So basically, I was in TEM mode and I collected diffraction patterns from the replica grating at different camera lengths. And you can do that with the EMPAD, right? I mean, it's 128 by 128 resolution. So the resolution is not great, but this is perfect as far as calibrating your EMPAD data, okay? So I did this for basically every camera length that I could, where I could still get meaningful, or I was able to still do it, right? So if the camera length gets too high, then you don't have enough information in the DP to do it. But if it gets too low, then like the rings get too bunched up and you can't delineate one from another, especially when your pixel resolution isn't great. So let's start from the high end here, and we'll work through some of these here and go down toward the end. Okay. So again, when you acquire a series, so this is a .raw file. It's not saying this here. So if you go to ImageJ, go to File, Import Raw, and then find the sequence here. And then again, 32-bit, 128 by 128, 1,000 images in the series, 1024 bytes between images. And we can go ahead and use a virtual stack, even though this is not a large number of images and they're not very big, but we'll go ahead and do okay. All right. So then what we're going to do now to improve visualization is we're going to do an average DP over the stack. Okay, so you can see as I scroll through here. So that's going to smooth out the shot noise. So you go to Image, Stack, Z project, and then average intensity. Okay, and then now what we saw in the video was by taking the log of this or the gamma, we can make it easier to see the features, okay? So let me go ahead and I'll just duplicate this. Image duplicate. Okay, so let's start by just taking the gamma, and we want to go to 0.5. Okay, and then now we have to readjust the contrast. So I did Control-Shift-C to pull up brightness and contrast. Then you can click Auto, and that's a big improvement. If we go to this other one and we do log, so you go to Process Math, log, and then you've got to do the same thing, Control Shift C, and this is probably going to be easier, or maybe not easier, but yeah, I think it might still be. I think this is still a slightly smaller dynamic range. Yeah, so this is even a little bit easier to see once you, okay, yes, once you do the auto, yes. So you can see here, right, my dynamic range here is 10.75 to 4 right? So that's very easy to see with our eyes. If we look at the same instance here, this is a lot higher dynamic range, but this is still, visible. So either one of these will work, to your preference. Okay, so let's go ahead and let's just use the log version here. I'm going to go ahead and close that one. And you can also, if it helps you, switch to a color lookup table. But now what we need to do is we need to look up the data for the replica grating. So in my Excel file here, this is the data, okay? So for the first 6 rings, these are the Miller indices, these are the despacing. This is the radius of the ring in diffraction space in terms of mrad. This is also equal to twice the Bragg angle, okay? So that corresponds again to this distance from the direct spot to the ring. Now the ring has width, so when you're measuring this distance, you're measuring it to the middle of the ring, okay? Because the ring is, has finite width, because the particles, have finite size. So you get some ring broadening, but that's how you're measuring it, okay? So because we can't, right, the direct beam's blocked off, the best way to do this is to measure from the middle of the ring to the middle of the ring, okay, horizontally here or vertically. So diagonally, it might be a little tough. It's better to keep it horizontal if you can, in my opinion. So in that case, that distance would be twice the radius in terms of mrad. The other way to do it is in terms of reciprocal nanometers, okay? So you can convert the radius to reciprocal nanometers simply by taking the radius of the D spacing for the ring. That will give you this. Or if you take the radius in terms of mrad, convert that to radians, and then divide by the wavelength of the electrons, which this is 300 kilovolt data, so this is 1.9687 picometers, okay? You should get basically the same answer either way, okay? All right, so we draw a line, and then I believe if you hold down, yes, hold down Shift, the line will remain straight. And then let me see if I can't. So now the beam stop is kind of over the line here. So it's a little, you kind of have to do a little artistic license here with this. But basically right about there. And then you go to analyze set scale. That's the distance we measured in pixels. So what's the known distance? So the known distance, again, is twice the scattering angle if we're going in terms of mrad, which would be 2 times 8.52 mrad. So if we do 2 times 8.52, we get 17.04. Get 17.04. Okay. So what it's saying here, whoops, and then, oh, I forgot something here. Sorry. Set scale, 17.04. The unit is mrad. Okay. Okay. So now it's telling us that the horizontal field width here is 17.41 mrad. Okay. So now we can come over here. We can input this number, 17.41. And then what I had it do here now is calculate the mrad per pixel. So this is just this number. Oh, sorry, I put this in the wrong column here. 17.4, or the wrong spot. This is the distance in mrad per pixel. This is the field of view in terms of reciprocal nanometers. Again, take this number, convert it to radians, divide by lambda, which is what you have here. And then you can convert this to, and then you can measure the value per pixel. Again, just this divided by 128. Okay. All right. So that's our first number down. So let me go ahead here and I'm going to turn off I guess we probably didn't need to use the lookup table. I'll just put this as gray here. But what we do need to do here is actually click apply if we want to save it with this adjustment. Oops. Why is it barking at me? Oh, apply does not work with 32-bit. Okay. I think we have to do set instead. Okay, let's see, adjust. Okay, set. Okay. Okay, so it's still not doing that. I think we just have to click set then. And then we'll do file, save as TIFF, series average calibrated. Yes. All right, so let's make sure that that worked. And it's 32-bit. It might not even open it well. Let me see here. Okay, so yes, it did this perfectly. All right, there's one down. Let's do a couple more here. So we'll go now to 1800. And again, as we decrease the camera length, we're going to see a wider field of view. Should get a little easier. Oops, sorry. Import raw series. Yep, everything's good. I'll close this guy. Okay, and then same thing, stacks, Z project, average. Okay, and then we'll go ahead and do math log, control shift C, auto. Okay, yes, so very easy to see. Now we can see the second ring here. So you always want to use the largest distance you can when you're doing these calibrations. That's going to give you a more accurate measurement because your relative error is going to be less. We can click set here. Okay, and then I'll go ahead and save as TIFF. And I just added, I'm overwriting these other ones. Okay, so then now actually we should have done the calibration, but that's fine. We'll do it now. All right, so again, hold down shift. Okay, and then again, this is going over the ring here, but that's fine. Okay, so middle of the ring to middle of the ring. So now if we go back to the data here, it's saying that the radius of the second ring is 9.84. So now we're going to do twice that. So we come back here. 9.84 times 2 is 19.68. Okay. (19.68) unit of length mrad. Okay. So now our field of view is 21.81. And now when we say it's going to keep the calibration now. So if we open this again, it's going to show mrad. Okay. 21.81. Okay. And we'll do a couple more here. Let's see here. Let's close that one and that one. Okay. Math log. It's a shame it doesn't do an auto adjustment to this. You have to do it manually, but yeah, the result is certainly worth it. Okay. All right. So we can't quite see the third ring, so let's keep going with the second one here. Okay. Something about like yay, I think. Another option you could try doing is using a a circle here. This gets a little bit trickier to do, but see, the problem with this is it doesn't do fractional numbers, so this is why I like using the line. Okay. Analyze, set scale. 19.68. Milirad. Okay, so now we're 27.38. Okay, looking good. And let's do 1150 here. Oops, sorry. It did open recent for me. Okay, stacks, Z project, average, math, process math log, Control Shift C. There you go, auto. Set. Okay, so now we can actually see the fourth ring here. Okay, I think we can do that accurately. So let's go ahead and use the fourth ring. Here again, the beam stops blocking it, but we can just have to make do there. About like that. Okay, so now we go back to our data here. All right, so the fourth ring is 16.27 millirad in terms of the angle. So we're going to double that. So we're going to do 16.27 times 2 is 32.54. Oops. Millirad. There we go. All right, 34.25 millirad. Okay, let me save this. I think if this was already set to be a TIFF, so it will auto save it as a TIFF. You don't have to do save as. I think if you just specify an extension, it will do that, which is kind of nice. Okay, since we're going quickly here, let's do one more at 910. And then we'll talk about the measuring the saturation current. Import raw. And then let me delete these. I can't actually, that's okay. Series. Okay, close that one. And then I'll open one of the really short camera length ones so you can appreciate how kind of tricky those are. Although maybe we can try and calibrate one just so we see here. Process, oops, sorry, image, stacks, Z project, process math log. Okay, so again, I think we can use the fourth ring here. Right about there. You can kind of see the direct beam pretty well. This is not entirely blocked off. So again, that's going to be the same number now, which is the 32.54. All right, so let's go ahead here. Okay, 42.94. 42.94. Okay. And then last thing, let me show you one of these ones at like 360, just so you can appreciate how this gets kind of tough when the camera length gets really short, just like when it gets really big. Import raw. Okay, so you can kind of see, right? So, I mean, it's tough to kind of make heads or tails of what's what here. I think this guy right here is the third ring, actually. Actually, so this is where if we have another one opened up, it's going to get a little easier to kind of make heads or tails of this. Let me go ahead and open. Let me go back here. Did I do one at 9:10? I did. That's right. Let me open this. Yes, so that's what that one is. That's actually the only one that's really distinguishable. So that's, I mean, that's not the farthest distance, but that's the most separated. So I'd probably use this one, believe it or not, to do this. Okay, so let's go ahead here. Okay, if we had a single crystal, this might be a little easier, but that can be a little trickier to do. I've never done that with the EMPAD. It might be a little, a focus spot single crystal, so I wouldn't recommend trying that. But we can go ahead and do set scale. And now this is now the third ring. So that's 13.96 times 2. 27.92. Sorry. All right, 113 mrad. Yep, 113 flat. Okay. All right. So now what I'm going to do here, I'm going to cheat a little bit because I actually did this before. I just want to see if my numbers are where I'm expecting them to be, just to make sure for my sanity. Okay, yeah, so they're in the ballpark here. There's a little more discrepancy as you get out into the shorter camera lengths, but yes, if you look here, these are all on target here, especially the higher camera length. Okay, so we're good there. All right, so no issue there. All right, so now the other part of this is the saturation current. So one of the things that you need to be careful of with the EMPAD is that you don't exceed the saturation current. So to help demonstrate this, and this is something I didn't have when I did the take one, so I recorded a series of just the probe in vacuum, and this was at 720 millimeter camera length. Okay, so not very interesting looking here. I'm going to do the same thing though with the Z project. Okay, and then what I've found here, so let me duplicate this so I can show you. So if I do log of this, okay, so we can see it not too bad there, but what I find with this one actually is if you do the gamma, this works a little bit better here. Okay, so you can see, right, that's just a little bit less saturated, although this is probably maybe overestimating this by a smidge here if I had to guess. But anyways, so yeah, pick whichever one of these you want. Again, what I mentioned right in the video, what I mentioned in the video was that the video on collecting the EMPAD data is you need to measure the angle beforehand. Don't rely on it in the software. But anyways, if we let's just use this one for the sake of argument because it's just a little easier to see here. So if I scroll in on here, you can see that this probe is encompassing a finite number of pixels here. Okay. So we want to figure out, right? We know what the probe current is, and we can figure out approximately how many pixels the probe is taking up on the EMPAD 2. Okay, so we can do that. We can try and measure it directly, but the easier thing to do is if we have an accurate measurement of the actual semi-angle of convergence itself, and we know the calibration data that we just got here, right, in terms of the field of view, in terms of mrad, we can actually calculate it and get a more accurate answer, okay? So the basic idea here is we have this equation. So basically 2 picoamps per pixel, okay? That's the saturation point. So that's equal to your maximum current divided by the area of your direct disk, okay? So if you measure alpha in terms of pixels, you can get your direct disk area in terms of pixels, okay? One of the things we're assuming, of course, is that all of your current is inside of the direct disk. When you do an actual experiment, that's not going to be the case, but we're just making that assumption here, right? So if we look at this, you can see here, if I draw a line, right, that would be, I know it's kind of tough to see on there, but that would be the, that yellow on there, but you can see like that would be the radius in terms of pixels, okay? And obviously that's a little tough to do, so, but that's the same idea here, okay? The radius in terms of pixels. So anyways, we can convert the radius in terms of pixel, or we can relate, I should say, the radius in terms of mrad to the radius in terms of pixels using this equation, okay? So if we know what the field of view is, which we calibrated in terms of mrad, okay? If we know this information, the radius in terms of pixels is simply equal to the radius in terms of mrad multiplied by 128 pixels divided by the field of view in terms of mrad. Okay, hopefully that makes sense, right? So this is just this right side, or this part here is just a reworking of this, okay? So you're getting alpha pixels in terms of alpha mrad and the field of view of the dp in terms of mrad. So then from here, it's just a matter of rearranging this equation so you can calculate I max, right? I max would be 2 picoamps per pixel times pi alpha pixel squared, and you can substitute alpha pixel using this, and this is your ultimate equation here, okay? So you have 2 picoamps per pixel times pi multiplied by 128 pixels times alpha in terms of mrad divided by the field of view in terms of mrad whole squared. Okay, so that's going to tell you what is my maximum probe current beyond which I'm going to saturate the EMPAD, okay, which you want to avoid. Okay, again, this is assuming, right, that all of the current is inside of your direct disk. Okay, and obviously, if you're in vacuum, that's going to be the case, but that's not going to be the case if you're doing diffraction, an actual diffraction experiment, okay? Especially if you have strong diffraction conditions, but, so they say, right, better safe than sorry. So anyways, we can calculate this very easily, okay? So I have another spreadsheet here. And so all we have to do is input the field of view that we calibrated, and it's going to calculate out these values. So let me go ahead and pull that from the other spreadsheet. Okay, so we have 17.4. Let me copy these, and I'm going to paste the values. Whoops, copy and paste values. There we go. Okay, perfect. Okay, so these three columns on the right, what do we have here? So this is the saturation current, assuming our value of alpha is 0.5 millirad, okay? So you can see the equation up here in the address bar, 2 times pi times quantity 128 times 0.5 millirad divided by B11, which is this number, the field of view in terms of millirad, and then that whole quantity squared, okay? All I did for the next one is I changed the value of alpha to 1, so I doubled it. So you see what happens is I quadrupled my saturation current, and if I double it again to 2, I quadruple it again. So this is a factor of 16 more than this. So what you see here is that as my field of view gets bigger, my saturation current goes down, okay? Saturation current goes down. And then what I'm going to do here again, just to check my sanity, because I already did this, is let me see if I'm getting similar numbers to what I was getting before. Okay, let me see here. That's 300. Oops, sorry, I had that. Okay, so I had an extra thing in there. So if we look right there, 85. Yes, so these numbers are on target. They're basically the same within a little bit of error, okay? If you look at these numbers here compared to these numbers here. And again, right, we didn't do those calculations, but yes, the rest of them are on target with a little bit of variation. So anyways, right, so what we see, right, is as we decrease the camera length, we increase our field of view in terms of millirad, and as a result of that, though, our direct disk is taking up fewer pixels, okay? It's taking up fewer pixels in the diffraction pattern, and so as a result of that, it takes less current to reach the saturation point. So when you're down here at your shorter camera lengths, you really only need a few picoamps until you can hit saturation, okay? And a lot of times when we're doing 4D STEM experiments, we are using values of alpha of 1 millirad or less, okay? So again, if you're doing short camera length work with this, this is something to definitely consider. Again, you can take into account the fact that you do have distribution to the non-direct disks, right? So again, this is assuming your entire probe current is confined to only the direct disk, okay? Which in reality is not the case, but this is kind of your better safe than sorry answer here, okay? So yes, that was what I wanted to share with you. Again, because I wanted to show the adjustment of the calibration data better, right? By taking the log and then adjusting the contrast limits, which I didn't really do well in take one. And then I wanted to explain the Imax or the saturation current calculation a little bit better, again, by showing this example, right, of the DP in vacuum. So you can see the direct disk, the DP collected from vacuum, where you can see only the direct disk, and you can see how this takes up some finite number of pixels, okay? All right. So anyways, that is take two. And appreciate you bearing with me here. So last day of August, we got 4 months to go until 2026. Take care, everybody, and peace out, my EM aficionados.